Hi guys, sorry for keeping you guys a little bit over. I'm going to keep on going through this problem for you so you can take a look at it as your leisure if it makes a little bit more sense than just looking at math on a paper. So for part C, we're asked to determine how big the centripetal force is while the satellite is in orbit. And it says explain. So the explanation part comes in saying, all right, we can figure out. So looking at the scenario, there's only one force. There's the force that the moon is pulling the satellite towards itself, towards the center of the moon. So that is the only force there. So that is its gravitational force, and it's also the centripetal force. So we mentioned, Newton's second law, net force being, not labeled in a force diagram. So since we do have a circular motion here, the satellite is moving in a circle. If we kind of said centripetal force as like net force, since there is only one force, that's going to be gravity. So then we can use our universal gravitation equation to calculate that. So we have big G, 6.67 times 10 to the negative 11th. And it's a Newton times a meter squared over kilogram squared. And that's just whacking units so that all the units cancel out and we're left with a Newton. So we have the mass of the moon given to us at the top of the paper. We have the mass of the satellites given in part A. All divided by our radius that was purposeful in part B to make sure that we had that big value. And we have to square that. So if you look, there's a lot of buttons you're going to have to push to enter this into a calculator. So the chances of being wrong are very high, especially if you're not sure how to use your calculator with exponential or scientific notation. So give me just a moment to plug this all in. And what you want to do is make sure that, obviously the setup is important, but knowing how to enter everything into your calculator as well. So try a couple times to get the answer that I'm going to put down. And if you have an issue, make sure you reach out to me at some point so we know what buttons you need to be pressing on your calculator. So I entered that all in and got a little bit over 2,000 newtons. So take some time and plug that into your calculator, that calculation, to make sure you can get that number. Part D is asking us to find the orbital velocity of the satellite. So it's moving in a constant speed around in a circle, right, in its orbit. Its velocity is changing. It's just a nuance of calling it like that orbital velocity or tangential velocity or velocity in a circle. So since from the first part we showed that Fg, force due to gravity, was our centripetal force, we can jump right into saying kind of the reverse. solve for velocity. So where that 2,175 newtons is going to be our centripetal force. So we have the mass, and this is going, so we got two masses. So what we need to make sure that we focus on is, what is the problem asking? We're looking for the orbital velocity of the satellite. So we're going to use the mass of the satellite, which was 1,500. This is the radius of our satellite that we figured out in part B. I'm going to do if we plug all that in, making sure that we take a square root of our velocity towards the end. We get around 1,633 meters per second, which, yes, that is very fast. 1,600 meters or 1,609 meters is technically a mile. So this thing is moving a mile every second. So in space, a lot of, satellites and planets, they're actually moving very, very, very quickly because of, that whole kind of radius. So even though it's taking 24 hours to orbit the Earth, the sheer, distance that they're traveling makes them moving very fast. So part E, how long will it take the satellite to orbit the moon? This time is called an orbital period. So at this point, I think it makes sense. Period is not abbreviated with a P, capital or lowercase, because they're already taken. So orbital period is technically the time it takes to orbit. So it's a time, but it's different than our regular time. So when we're looking at like the period of an oscillation or rotation, we use capital T. It is a type of time, but it's a specific time for something to happen. So that's what we're looking to do. So let's see. So we're looking at the basic scenario of velocity is, or speed, distance over time, which the distance is circular. So kind of like our lab, it was the circumference of a circle, 2 pi r. We're looking for the period. So we know the velocity was 1,633 meters per second. It's going to equal 2 pi our radius that we had before. And we can solve for our period. Hit the wrong button, sorry. Which the period call it 80. It's about 7,000 seconds, which if you divide that by 60, that's about 118 minutes. Divided by 60 again, that's about 2 hours. So it takes this satellite only 2 hours to orbit the Earth. And there's a lot of satellites that are moving this fast. You got weather satellites, you got, anything that we're using consistently. 6, if the satellite is this satellite accelerating while in orbit? The answer would be yes, and we know that because it's changing direction. It's not necessarily speeding up or slowing down. It has centripetal acceleration. So in the second part of the question, what is the direction and magnitude of this acceleration? So the direction is towards the center of the moon, inward to that circle. And the second part of our circular motion equation, the v squared over the r, is centripetal acceleration. And that equation is located on your AP Physics equation sheet. So our velocity that we had divided by our radius. Forgot to square my velocity. So it's about 1.4 meters per second squared towards the center of the moon. So hopefully that was good enough to finish. Make sure that you work on a little bit each day or every other day. The homework that's going to be due Wednesday and Thursday. Wednesday, the questions are due, so questions and misconceptual questions. That's posted on Schoology. And also Thursday, the problems will be due. So budget your time accordingly so that on Tuesday night or Wednesday night, you don't have an hour or more's worth of work to do. Have a good weekend.